3, we're actually going to get into the integral. And here is the sign, the little summation sign that's kind of curved. And we've got some parts. And this is talking about the parts. Can you guys see that at the back? You can see the writing. I can make it a little bigger. Is that better? All right, so here's the upper limit of the integration. Here is the lower limit. That, of course, is the integral sign. This is the function. And then this says x is the variable of integration. And you should always see a dx if that's what we're integrating with respect to. And this is saying this is the integral from a to b. In that previous section, we were beginning to look at this is from this to this, and we're going to take the areas of these rectangles. Well, now we're doing the whole process. I think you'll find it not nearly as bad. Yes, ma'am.
Could you explain some of those terms, like the integration? I'm pretty sure you explained it before.
Integration is, well, remember last time we were talking about integration is when you're going to take actually the limit of the sum of those rectangles. Think about that. We had, and I really, when you go on the lecture notes for 5.1, there is that, remember I said there was that link to a website, an interactive website to go to? And what it has, you can put in any curve and you want. What we use this for, like if I had this curve and I said it was from here to here, and I wanted, say this was -2 and this was 8, and I said, okay, I want to find the area under here, the area under that curve. We don't have any formula for that curve. We don't know what that is. It's not like we can say length times width. But the idea is if you put a lot of rectangles in here and you took the area of each rectangle and added it up, took the sum of it, you could get pretty close to the area. Integration is saying we're taking the limit as that number of rectangles goes to infinity. And so we're summing up all those little areas. Except we're not going to be taking rectangles and areas. We're going to have a process to do this integration. Is that better? And as we do it, I think it will make more sense. But that's what's happening. You're going to say the integral from -2 to 8 of whatever that curve is, say it was x to the 4th minus blah, 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 blah. And we have a way to integrate. We have some rules to integrate, and we'll be finding the area that way. Okay?
So by doing it with the limit to infinity, that's making it as accurate as possible.
Mm-hmm. Mm-hmm. As accurate as it gets.
Yeah,
okay. All right. Can I move, or are we still writing? We're good? Okay. So here's some rules. You don't need to write these down, but they're there for you when you go look on the notes. This one seems to be pretty important. We will use this not so much in this section, but maybe in later sections, that if you have a constant multiplied by a function here, before you start integrating, you can pull that constant through the integral sign. You can't pull a function through. You can't take an x out, but you can pull a constant out, and that will make it easier for you sometimes. So that's one rule. And the rest of those are just kind of basic things. So just read those when you get a chance. Now, they're not the rules that are on your sheet. Your sheet that has derivatives and integrals, and we're not really getting to all of the integral rules today, but you need to bring that sheet with you next time. Okay? All right, but in this section, we're just going to get started with this. And so we will use this formula, possibly. Okay? Area under a curve is what we just said. A is equal to the integral from a to b of f of x dx. If they say, find the area of the curve, you know you're just going to take the integral. Okay, you're going to take the integral from here to here, under this curve, using that function, you're going to get the area. Okay? And I wouldn't worry so much about this. I would write area under a curve, and here's this formula.
That's the most basic.
It is the most basic.
That's why it's not on here, because
Yeah, yeah. All right, and then the other one is if you want to find the average value of that function on an interval. If it's integrable, that means if you could take the integral of it, then its average value on a, b, you find the integral, and you multiply it by 1 over b minus a. So if you were taking the integral from -2 to 8, you would take the integral, whatever the function was, but then you'd multiply it by 8 minus -2. So you'd multiply it by 1/10, whatever that other integral part ended up being. Does that make sense? 1 over b minus a. Okay? All right? And really, these problems, for those of you that know how to do integration, you guys that have had calculus, these are going to seem really, really easy and not really what you're used to because we're not quite there yet. Next section we will be, and somebody asked me if this was going to get harder. The hard part of integration, and you tell me if you agree, the few of you that have had it, would be maybe substitution, when you're integrating by substitution. Do you remember, Cody? You don't remember that? Okay. Keith? Because it's not apparent sometimes how you do the integral, and so you have to let u equal something, and then you do du and all of that business. Do you remember that? That to me is one of the harder parts, and that's one section. And one of the instructors that teaches Cal 2 on a regular basis said that that was something that was really important that you saw a lot in Cal 2. So we'll definitely cover that. Okay. All right. Let's look at the problems. There's a few. There's not very many. All right. And when you look at these problems, I do not want you to get all wound up about all this stuff. Okay? All right. This says express the limit, and here's the limit. What does this symbol mean? A sum of. So aren't we going to be doing this integral thing? It has a constant, and then it has k, delta x, blah, blah, blah. It has a bunch of stuff. P, a partition of. So what does this remind you of? Is that the interval? Okay. As a definite integral. And here's how the problem will look in Math Lab. So it's wanting these upper and lower limits. So what's going to go down here? Okay. And 11. All right. Now, this thing, this C sub k, see if I can, this part right here, you want to typically, for these problems, think of that as x. That C sub k. We're just going to say that's that. So it's that to the what? Can you read that number? Fifth. So, x to the fifth. And you also need to put your dx there. And so it's saying this thing, C sub k to the fifth, the delta x thing here, that's the dx. We're going to say that we're going to use that. We're going to call that dx. And so when we're filling these in, that's how you're going to think about that. Okay?
The change in x,
Mhm, the-
derivative,
right.
slope to slope.
Right. And when you see that, when it's a dx, you know that means, oh, I need to come up with something that I would get the derivative, if, you know, because we're working backwards now. We're working backwards. All right, let's look at number 2. Express this limit where p is a partition from 2 to 6. Without looking at the multiple choices, let's just look at this. We would have the integral from what to what?
2 to 6.
2 to 6. 1 over 2x dx. And so that would be choice here. Okay, so I'm just getting you used to thinking about that it's a limit, but we're putting it in the integral form. But pretty easy. Okay? All right. Here's this one. Integral of what to what. So what's going here? Negative pi over 5 is going here, up to pi over 7. And what is our function? tan x dx. Okay, are we okay? All right. Okay, now we're going to use some of those rules, but it's not. I need to make this a little smaller so we can fit it on the screen. Okay. All right. It's giving you three little functions here. So we've got this one, and put it in yellow, and then we've got this one, and then we need another color. Can you see it if I do that in green? Can you see through the green? Okay. All right. So we've got those three things. All right. And we're just asked to think about something. If we're going from 4 to 4 of f of x dx, there's a rule. If you go from the same number to this one, what is the value of that? 0. Okay, so that's kind of just a rule. And the deal was this 4 and 4 being the same thing. You're not moving anywhere. Okay, you're not going anywhere. So there's no sum. It's 0. All right, for this one, from 7 to 2, g of x, which one of these guys is g of x? This last one? Okay, does this go from 7 to 2? 2 to 7. If it's the same function, but you have the limits of integration reversed, what would you think happens to the 5? Okay, so this is negative 5. Does that make sense? If you reverse the limits of integration, it's going to change the sign of your answer. Okay? All right, how about, oh, we need to have those always showing. All right, we have 2 to 7, 9, g of x. 45, because here, g of x, 2 to 7, was equal to 5. We had this constant. We could pull it through, so it's 9 times whatever that value is. So that's 9 times 5, which is 45. Does that make sense? Okay. All right. I keep wanting to move. All right, from 4 to 7, f of x. 4 to 7, f of x. Do we have one of those? No, but we have 2 to 4, and we have 2 to 7. So what we're going to do, we can say the integral from 2 to 7 minus the integral from 2 to 4. The bigger interval, subtract the smaller interval, and don't we ultimately, if we've got these two numbers involved, we're going to be okay. That's the rule we're going to use. Does that make sense? Because we don't have one that says from 4 to 7, so we're going to do this. So what is the integral from 2 to 7 of f of x? 8. So this is 8 minus this guy. Okay. And the last one, we've got from 2 to 7 of g of x minus f of x. So what do you think we can do? Can we just subtract them? And do I have another one, or is that the last one? One more. Okay, 8 of the g minus f. 8 of the g minus f from 2 to 7.
40 minus 8.
So 40 minus 8, what do we get? 32. Okay. As long as you get the process that you are looking at these that are given, checking the limits of integration, seeing if they're the same, seeing if you need to manipulate something, or you can multiply constants and that sort of thing. Okay? So we're good. All right. Let's go back. How far? That? Okay, that's good. I'm going to ask that you try number 5. So if you guys want to write down, it's just got one integral. The integral from 6 to 7, f of x dx equals 5. This one?
No, the third one.
This one?
Yes.
Mm-hmm.
The reason that works is because you're taking the bigger area and subtracting the smaller area.
Right, right.
Okay.
Big picture?
Makes sense.
Good. All right. Okay. So here's the one that I would ask that you try. This is essentially the same thing as that. Doesn't matter if the letters are the same. Let's use that as a basis and see if we can get some numbers. What do we get for this one?
Why they change the letters?
They're just trying to get you to see that it doesn't matter what the variable is. If we're given that this is equal to that, find the value of the following, and it doesn't matter that if it's f of u du or f of z dz or whatever, if we're going to call it the same, different letters, it's okay. But we're using these rules. What would happen here? What do you get?
5 restored to 6.
Yeah. It's just another way to use those rules, Dinah. Okay, what about from 7 to 6 of ft dt? Okay. From 6 to 7 of negative f of x. Yeah. Okay. Because this was negative of this. Yeah. Okay? All right. Who knows what a trapezoid is? What is it, Lucas? You did a roof thing. Okay, so it has parallel bases.
Pizza Hut.
Pizza Hut. Okay, that's good. All right. All right, so number 6. Let's see if we can get a little bit of room here. So, was this the one? Oh, we're not to the trapezoid. It's the next one. Let's do this one. Here we've got this guy and this guy. All right. This is from 0 to 5. This is from 0 to 6. So now we want from 5 to 6. So the integral from 5 to 6, what are we going to do? 0 to 6 minus 0 to 5? Okay, so what's that going to be? 6 minus 3? Okay. And if that's what 5 to 6 is, now they've changed the limits of integration from 6 to 5, negative 3, because of that being the opposite of this guy that we found. Okay? All right, any questions on that?
Do
Okay.
you always take, when you have one like
This?
the one Drew asked about earlier,
Mhm.
and the one right there, you always is it always the bigger?
Yes,
minus
because
the
you've got to
small?
subtract the bigger area, the smaller area from the bigger area. Yes, sir.
So if you didn't have the A, would you have done 3 minus 6 on D?
Yes, you could do that. You could do. All right, here's the one with the trapezoid. Okay, on your homework, it will ask you to graph the integral. Well, the integral is this part in here. So I did that on the calculator and brought a screenshot in. So I just went to y equals and put x plus 6. And it says over the integral from negative 4 to 6. If you wanted to see just that picture on your calculator, what would you do? What would you change?
Window.
Window, and what part of the window? From x min of negative 4 to an x max of 6. And then you would get this exact window there if you wanted to see that. All right, so I've got that piece, and it doesn't graph this little line here, but I drew it in, and there's a little bitty one right here. So I definitely have a trapezoid. I have parallel bases here, and I have these parts in here. It's kind of a this way trapezoid. Anytime you have parallel bases and these parts are not, then you've got a trapezoid. All right. It says we want to know the value of this by determining the area of this thing. Well, right now we don't know all our rules yet. But if we know about a trapezoid, we could do this. Do you know what the trapezoid area formula is?
Base 1 minus base 2.
It's half the sum of the bases times the height. Okay? So half the sum of these numbers times the height. And the height would be the distance between the bases. All right, so How did I know that this base was 12?
Because if you take the x value,
This x value right here, x is 6. And if I do f of 6, that means plug it in here to the line. 6 plus 6 is 12. So that means that y value right there is 12. Okay? And right here, my x value is not a positive 4, a negative, well, that's not that thing, is negative 4 right here. So plug in negative 4 and you would get 2. So the height there is 2. So then, what's the base? What is this length? How did I know that that was 10? Because from there to there was 6, from there to there was 4 units, so 4 and 6 is 10. So the distance between my bases was 10. So over here, A equals 1/2 times 12 plus 2, all of that times 10. So what is my area? 70. Okay. All right. Questions on that? I gave you the trapezoid formula, so in case you'd forgotten that, you've got that. Okay? Anybody still writing? Amber, you got it? All right, same thing with this one. And I graphed that, ended up being a semicircle. And so what can we use to find the area? 1/2 pi r squared. Okay. And how did I know this was 10? Was here's my limits of integration from negative 10 to 10. And so that means my radius for this circle, and it doesn't look like a circle because of the screenshot that I took, but the radius would be 10. So you've just got A equals 1/2 pi times 10 squared. So A is 50 pi. Okay. And you would leave pi in your answer because here in the directions, and this is important, it says type an exact answer using pi as needed. If they want an estimate or approximation, then you would use 3.14 or your pi button on your calculator. But if it's exact, you leave pi in the answer. Okay? All right. This one I omitted. It is not in your homework any longer. So just forget that one. Any omits are good, right? Okay. Now we're going to start actually using the little rules that we know to integrate. All right? So here's the way I would approach these, and they're really pretty easy to start out with. Take this integrand here. What is the integral of x? What did we learn? What do we do? Don't we? We increase it. So the integral of x is x squared over 2. Okay? We don't have a plus c anymore because we have definite numbers that we're doing it on. And so then I like to write it, I'm going to evaluate x squared over 2 at both the square root of 14 and 3. Okay? So what does that mean? You evaluate this top part first. And so I'm going to have the square root of 14 squared over 2, and you subtract it evaluated at this point. Okay? So what's square root of 14 squared? 14. So this is 7 minus 9 halves, which is how many halves? Because that's the same as 14 halves, right? Questions?
How do you get x squared?
How did we do this? Remember when we said we were going to integrate that basic rule, you add 1 to this exponent, which makes that 2, and divide by that same number? Yes, it's a rule. All right. Are y'all still writing? Are you good? You good? Okay, let's do this one. Same idea. This has got theta d theta. What is the integral of theta? Okay? And so we're going to evaluate theta squared over 2 at 4 pi and pi. Okay? So we got 4 pi squared over 2 minus pi squared over 2. So what do we get there? We get 16 pi squared minus pi squared over 2. And really, that's all they're wanting you to do at this point. Just getting you the idea of find the integral and then evaluate it, and you subtract upper limit, subtract the lower limit. Okay? All right. You try this one. Do the integral of t squared. What's the integral of t squared? T cubed over 3. Okay. So we're going to evaluate t cubed over 3 at 9 halves and at 0. Why is this to the third power? You always, when you have just a plain thing like this, you're going to add 1 to this and divide by that same number. Okay? And remember, Dinah, if we wrote this as 1/3 t cubed, now take the derivative of that. 3 times that would be 1 t squared, which is what we have here. It has to work. Okay? All right, so what do we got? We got 9 halves cubed over 3 minus 0. Yeah, you have to be careful with the 0. It's not always that part just goes away, because if you were evaluating certain functions, the 0 might still play into it. It might not go away. So just be careful.
There was a constant in there or something.
Yeah, all kinds of things could happen. All right, so what did we get here?
2, 3, 3 over 8.
That would be the reduced final answer. Okay. Okay. All right. Okay. How about that one? Integral from 6 to 3 of 4 dx.
So it's just 4 I
Integral of 4 is 4x, and so you're evaluating 4x, 3 to 6. So let's see what you get.
Probably just 4 -12.
Mm-hmm.
Because it really limits it. Just a constant. You just because if it was 4x, what's the derivative of 4x? Yeah.
So anytime you see a constant, you're just going to add the variable on there. All right, everybody good? Okay, they give you all this business here. Here's the integral that you're going to evaluate. So let's try that one. Mm-hmm. Integral of 2x is 2x squared. Now really, this is where, and it's not bad here, but when you have the integral of 2x, you can pull that through, and so it's 2 times the integral of x, and that's why we have 2x squared over 2, which is x squared. And you evaluate x squared at 1 and 0, so that's 1 minus 0, which is 1. Okay. All right, I think we have one last one, and I want you to do it by hand, and then we're going to do it by the calculator. All right, so do this one. Little bit more involved, not much. We're still on the easy baby ones. should come out as a whole number.
285.
Mhm.
Yes.
It's going to black out for a minute. Sorry. And that's not bad, but some of them do get pretty tedious if you're doing definite integrals with big numbers or crazy functions that you don't want to plug in. So we do have a way to do those on the calculator. So let's kind of go over that. We'll do this one with the calculator and make sure. Oh, and you guys probably have it where it just, yeah, it's perfect.
Just tell it to come. Just
Yeah. Second math, not second math, sorry. Second quit. Let me clear out of where I am. Math. What's the number? Oh, I went too far.
yeah.
Math and number 9. It has FNINT. It's numerical integral. So you're going to choose that. We're going to put in the function. So we're going to put in 4x minus 1. We're going to put a comma. We're going to put x, which is the variable. We always have to put that in. We're going to put a comma. And let's put the lower limit, 12, and comma, then the upper limit.
So it's just like the other one. It's just the same.
Mm-hmm.
It's function, variable.
Yeah. So that comes in really handy if I gave you a horrible thing to integrate, but it was a definite integral. Then you could just throw it in there and get the number. And when that comes in handy is maybe an application problem that had some other things to do, and you could just do that part on your calculator. I will let you know if it's okay to do that or if I want to see all the work. Some of them I'm going to want to see the work, but the bottom line is if I really want to see how you integrate, it probably won't be on a definite integral. It will be on a just find the integral of this, and it'll be an indefinite one with the C. That shows me that you know how to integrate. This, the part that gets tedious is plugging in, and that's just the algebra of it. Okay? So any questions on that so far? Okay.